Hello friends, welcome again to the tetrahedron chemistry classes. So in the lecture series of PYQs of spectroscopy, today I am going to discuss 8 problems from the 2014 CSIR NET examinations with a detailed explanation. Okay, so my first question, if you can see here, what the question says: the correct match of the proton NMR chemical shift of the following compound 1, compound 2, compound 3. You have been given 3 compounds and you have to identify actually what is the correct order of chemical shift for the following compounds. You have been given the 4 options A, B, C and D. So how we can decide this thing? So first of all, see what is the way to solve this question. If you focus on this cyclopentadiene, okay, so this cyclopentadiene is basically having 2 hydrogens here, 1 hydrogen here and 1 hydrogen here and another hydrogen here. Okay, so 1 hydrogen you can put here, another hydrogen you can put here, another hydrogen you can put here, and next hydrogen you can put here. So these 4 hydrogens are of the same kind, so they will produce the one signal in the proton NMR spectrum, and another signal would be due to these 2 hydrogens. So basically this will give the 2 signals in the proton NMR spectrum. But you can see in the question itself, it is not given that how many different signals are there. So we can straightforward discard this option number 1. Why we can discard this option number 1? This cyclopentadiene, basically this carbon is what you see. This carbon is your sp3 carbon. Okay, whenever you have the sp3 carbon, it is non-aromatic. This compound is non-aromatic. And non-aromatic compounds, basically it is the kind of the CH2. So the signal of this should be quite upfield, somewhere around 1 ppm in the proton NMR spectrum. But as you can see in the options given, no chemical shift is near to this value of 1 point, or say between around 1 ppm. So we can immediately discard the option number 1. Okay, but if you focus on the another things like your second molecule, you know the hydrogen is here, hydrogen is here. So this benzene is having all the hydrogens, right? Okay, all the hydrogens it is having. So it will produce one signal in the proton NMR spectrum. Definitely it will produce one signal. Okay, and you know benzene protons resonate around your 7.0 ppm. Okay, so for the second you have to look for the 7.2 ppm. So straightforward you can discard the option D, because second compound is having the chemical shift of 9.2, which is not the characteristic of the benzene. And on the same ground you can discard the option C also. This is also not correct, because here also again you can see of compound 2, that is the benzene, its proton is showing 5.4. So these 2 options cannot be correct. So now what left is option A and the option B. In the option A, benzene 7.2, benzene proton 17.2, and in the option 3, benzene proton 7.2. So either A or B, right? Both C, out of these 2, anyone could be correct. Now we can decide the chemical shift, right? And this is your tropylium. This is your tropylium cation. This tropylium cation is also aromatic like benzene, and it is also having the different hydrogens attached to it. But you know, due to this positive charge, positive charge means electron deficiency is there. Whenever electron deficiency is there, that means electrons are not here to shield the hydrogens from the external magnetic field. So the signal would be quite downfield actually, right? So when you compare your benzene, your tropylium cation, then the most downfield chemical shift of the hydrogens of tropylium cation would be the most downfield. So you have to look where the third option is having the highest downfield shift. So you can see this is option number 3. This is option A, and this is the compound 3, which is having the chemical shift of 9.2. This is option B, this is the compound 3, and the chemical shift of 5.3. Clearly you can see the option A is having that third compound, which is the tropylium carbocation is having the higher chemical shift. So it is looking like that option A is the correct option. Okay, so you can immediately mark option A as the correct option. Okay, so this is how you can solve the problem. This problem basically based on your aromaticity as well as the knowledge of the proton NMR spectrum. Okay, now moving to the next problem, what it says. Second problem says that the correct 13C chemical shift values of the carbon labeled as A to E in the following esters are. So this is the ester molecule, and in this ester molecules you are having the different carbons. Now we are discussing the carbon NMR, like this is Me, this is CH, this is CH, this is another CH, right? And this is carbonyl carbon. So straightforward, what we can do, we can focus on this carbonyl carbon, and this carbonyl carbon belongs to the ester. So the key is that, see, if you want to solve this problem, so I can write solution here. To solve such question, or this not such question, this particular question, you have to focus on the carbonyl carbon of the ester. And you know, when the carbonyl carbon belongs to the ester, in the carbon NMR spectrum, it's generally its chemical shift ranges from 170 to 185 ppm. This is carbon NMR scale. Okay, now we have to look whether this 170 to 185 is given for the carbonyl carbon or not. This carbonyl carbon is marked as the B, right? So this is B, and see, for the B, that means for carbonyl group, option A is saying that it is 143. It is not actually in the range of 170 to 185. So you can immediately discard the option A. This option A cannot be the correct answer. On the same ground, if you look the second one also saying that your carbonyl carbon, that is B, which is this one, is having 143 of chemical shift. Again, it is not in the range of the ester carbonyl, so you can immediately discard this option also. Now look for the another option. See, option C is saying that okay, it is 167, so it is quite close to 170. Okay, so this could be your correct answer, option C. And on the same ground, your option D, you can see, okay, again it is giving 167, so this could be also be the correct answer. So out of C and D, one would be the correct in this case, but carbonyl carbon cannot decide the result actually, right? But however, the carbonyl carbon chemical shift is sufficient to exclude the two possibilities of A and B. Don't forget that in the NMR spectroscopy, nothing is absolute, all things are relative. So please don't say that it is 167, it is not in the range of the 170 and 185, right? So if it is 167, even if it is 165, it is quite sufficient to say that it is the carbonyl carbon which belongs to the ester. Okay, now we can see the which one is correct, option C or option D, right? So now you see here, this is your oxygen and this is your methyl, and this methyl carbon, since it is connected with the oxygen, so it should be downfield, and it is 52 here, it is 52 here. Okay, fine, it is again downfield, so this cannot make the difference. So these two, this data is not sufficient, as well as this data is not sufficient to distinguish between the wrong and the correct answer. Okay, but you can see here, what we can do, we can focus here. This is your carbon, alkene carbon, right? Option C, this carbon is the alkene carbon, and this carbon basically is highly shielded, so it should be actually upfield. So we have to look for the position of this particular carbon, whether it is upfield or not. Okay, so how upfield, how we can check option C. So this is your C, and now see, this is 143, this is 125. So between 143 and 125, 125 is the upfield. So it seems that the option D in that case is looking the correct answer. So what you can do, you can mark option D as the correct answer. If you want the little more investigation of this, so you can draw the resonance structure of this compound also, right? Like I am drawing the resonance structure for this one. So this will move here, okay, and the result would be like that. This is double bond O, this is oxygen, this is Me, and now you see here, because it because this has shifted here, and this will go up. So this is now double, and of course this would be single, so I can remove one of the bond from here, and it is negative. So this is the positive charge over there. Okay, positive charge, that means for the carbon D, and you know the positive charge shows the deficiency of the electrons, that means the de-shielding. When electrons are not here to shield the nuclei, that means the de-shielding would occur, and de-shielded nuclei, whether it is carbon or the hydrogen or any other NMR active nuclei, they appear as the downfield. So this actually this carbon, right, which is basically D, it should be the downfield, that means higher, it should have the higher chemical shift. So check, this is the carbon D, this is 125, this is 143, 143 is the downfield shift. So this further confirms that your option D is the correct answer. This is how you can solve this question also. Now moving to the next problem, what it says. Okay, now my next question, which seems that it is looking little bit tricky actually, but we can think that how we can solve this problem. Anthranilic acid on treatment with isoamyl nitrile furnishes a product which displays a strong peak at M/Z76 in its mass spectrum. The structure of the product is whether A, B, C or D. Which one is the correct? So guys, this question is not basically related to exactly the spectroscopic technique, but it is related to the spectrometric technique, and that spectrometric technique is hinting that you are having the M/Z value of the 76. So if you have seen my lectures on the NMR spectroscopy, then it would be easy for you to actually understand this kind of the problem, but for this you have to have idea about the basic organic chemistry also. So how we can solve this problem, we can see here. Say, first of all, you should know the structure of the anthranilic acid. Okay, so what is the anthranilic acid, guys? Anthranilic acid is nothing, you see, this is the benzene. Okay, just like that, this is the benzene ring, and this benzene ring will have C double bond O, OH, which is the acid. Okay, and at the earth position you will put the NH2. So this compound is the anthranilic acid. And from here, if you have the idea about, see, you have to guess many things before solving such kind of the questions. You have to play with your instincts actually, right, what you have learned so far. So in that case, you can see this is the benzene ring. So if you check what is the benzene ring, this is simply benzene. Okay, formula is C6H6, and if you check the molecular weight of this, so it is 78. Molecular weight is 78, and if you remove one hydrogen from here and one hydrogen from here, right, so it will give you the value of the 76. That means basically two substitution is there on the benzene ring in order to get the M/Z value of the 76. Okay, so basically this is the process of this is the one of the synthetic way to prepare actually the biphenyls, right. Biphenyls, as you know, biphenyls are very difficult to synthesize, and this method is anthranilic acid reacting with the isoamyl nitride is basically a method to synthesize the biphenyl. Okay, so how we can do this? So I am not going to give you the detailed mechanism, but I am explaining you. If you have the isoamyl nitride, okay, so isoamyl nitride is quite actually simple to draw. How you can draw the isoamyl nitride? This is 1, this is 2, this is N, this is double bond O. Of course, you should have substitution here. So what will happen in that case? You see, guys, this COOH will remove from here, and this NH2 will form a diazonium type of the compound. Okay, so I'm not actually discussing the pretty much the reaction in the pretty much detail, but I am telling you, if you remove this part from here, so what I can do, I can say this is the case, say this is COO negative, right, and this actually is your nitrogen. This is basically it is N2 positive. Okay, so what can happen in that case, right? So what I can do, I can make it little bit clearer to you. This is carbon double bond oxygen O negative. So in that case, this is a very famous reaction actually. If you heat the system, right? So what will happen? This will come here, and this bond will shift here, and this bond will come here. That means the nitrogen will remove as gas from here, and carbon dioxide will also remove as gas from here. And when these two have removed, then you left with this species. This one double bond was already there, another one is coming here, so it's a benzene. This is the benzene. So benzene mechanism is following here. Benzene is having one hydrogen here, another hydrogen here, another hydrogen here, another hydrogen here, and 6 carbons. So basically benzene is C6H4. So 12 is the atomic weight of the carbon, and the 6 carbons are there. So 12 into 6 is 72, and 4 hydrogens are there, that means 76. So benzene is there in that case. And if you have the 2 such benzenes like that, so cycloaddition kind of the reaction can occur from here. This is one benzene, this is another benzene, okay, and here you can check for the reaction which is kind of the cycloaddition. This double bond will come here, and this will go there, and this will result in a compound which looks like, see, this is double, this bond and this bond, another benzene here, okay, and of course one double is here, another double is here, this. So this compound is the biphenyl. So this option A is looking the correct one, and the 76 is hinting towards the benzene formation. So this question, however, is not that simple. For this you have to actually, if you have learned this synthesis of anthranilic acid, only then you will be able to solve such questions. Otherwise it would be very difficult for you to solve such kind of the reactions. Okay, now moving to the next question. So the next question says, guys, an organic compound gives the following spectral data. IR spectrum gives stretching frequency at 2210 centimeter inverse and 1724 inverse, okay, and proton chemical shifts are there. 3 proton triplet at 1.4 ppm and 2 proton quadrate at 4.4 ppm, and these are the carbon chemical shifts, okay. So again what you can do, you can check the frequency which is actually close to the certain carbonyl or not, right? So if you focus on this 168, okay, and I already told you that mean I already told you esters have the carbonyl frequency between 170 to 185, and this 168 carbonyl frequency is quite close to this one. So you have to look for the ester actually, right? But if you see, if you check the ester in that case, so this is the ester, this could be the answer. This is the ester again, this could be the answer. This is the ester, this could be the answer, but this is not the ester, okay, this is not the ester. So you can immediately discard the option 4. This cannot be your answer, okay. Now you can investigate further the stretching frequency, which is actually right. And one more thing, you see this 1724, right? It is also indicating that your carbonyl group is there actually, right? 1724. So this carbonyl is correlating with the 168, right? This is for the ester actually, okay. But if you focus on the 2210, right? This 2210 is the characteristic of the cyanide stretching frequency. So please remember, if you have this value around 2210 centimeter inverse, it is basically showing the stretching frequency of CN. That means your CN is there in the compound, okay. So you can check here, CN is there, so A could be the answer. And in case of the B, no CN is there, so you can immediately discard the option B also. Now look for the option C. Option C is having this cyanide. And furthermore, you can see the option C can be discarded. That means you see this carbon triple bond carbon is there, and we are not having this carbon triple bond carbon frequency in the IR spectrum, okay. And moreover, no carbon chemical shift is belonging to this carbon triple bond carbon, so you can immediately discard this one. See, you know this, if you have NH2 in your compound, so NH2 is having the little different chemical shift, right? Say not chemical shift, very sorry, that means frequency. This NH2, right? If you see this NH2 actually has the frequency near to the 3200, okay, and this 3200 centimeter is not there, so you can discard this one. So your option, either option A or option C, out of these two, one is correct actually. Okay, so which one is correct, we can immediately conclude this particular result. So what is there in the spectrum? You see, these are the 2 hydrogens and these are the 3 hydrogens. Similarly here also, these are the 2 hydrogens, these are the 3 hydrogens. So for this one you should have 3 proton. So it is actually little bit difficult to write in the out of the scale. So I am writing here. Okay, this will give you 3 proton triplet. Okay, no problem in that. And this will give you 2 proton quadret. So check whether this 2, for this also, this will also give you 3 proton triplet, and this will give you 2 proton quadret. Why 2 proton quadret? Because 2 protons are here. So I didn't write hydrogen here, but please note that hydrogens are there. Okay, because see, slide is quite crowded, that's why I haven't written the hydrogens over there. So 2 hydrogens are here, these 2 hydrogens are connected with the 3 hydrogens, so n plus 1 rule, 3 1 plus 1 4. So these 2 hydrogens, that means 2 hydrogens, this will give you the quadret, and 3 hydrogens are there. In the neighboring carbon you are having the 2 hydrogens, again n plus 1, that is 2 plus 1, that means triplet, right? 3 proton triplet. So both are giving same kind of the pattern, and you see in the question itself it is giving that triplet, 3 proton triplet, right? 3 proton triplet, and your 2 proton quadret, 2 proton quadret. But what you can do, you can focus on the chemical shift. You can immediately focus on the chemical shift actually, right? So in that case, you see the quadret. Quadret means the signal for these hydrogens, these 2 hydrogens as well as these 2 hydrogens. They are this signal is quite downfield at 4.4. Okay, and this signal is quite downfield. So what I can do, I can write the chemical shift for this one. For this it is 4.4 ppm. Okay, here also it is 4.4 ppm. Okay, but you know this CH2 is connected with the carbonyl. This carbonyl is actually the electron withdrawing group, so it will deshield the nuclei and causes the downfield shift for these 2 hydrogens. But again you can see here this oxygen is also very highly electronegative, so it is also actually the electron withdrawing group. Both are electron withdrawing, but you know this electronegative oxygen has quite important role in causing the very far downfield shift. So this carbonyl will also cause the downfield shift, this oxygen will also cause the downfield shift, but this oxygen is having more electron withdrawing nature, so this will actually shift the signal more downfield, and more downfield signal means that is 4.4, right? So 4.4 is possible only in case of the in case of the C, but not in case of the A, because it is not, this carbonyl group is not that electronegative. So it seems that your option C is looking correct one, so we can mark option C as the correct option. And one more argument you can see, one more argument you can do why this is actually 1700 at 1724, or what you can say why it is at 168 ppm, because you see this position is having the electron withdrawing group, so this will suck the electron density. Okay, and this will become weaker, right? This bond due to this resonance it will become weaker, and when it will become weaker, so it will show the lower frequency, and this lower frequency is 1724. Otherwise it would have 1700, it's around 1750. Okay, so this is how you can solve this question also. Okay, now moving to the next problem, what it says, My next problem says, guys, a compound with formula C4H6O2 shows band at 1770. Again, it is the ester. See, esters. See, guys, this carbonyl group is very important. Okay, and most of the time, this carbonyl group may present in the aldehyde, it may present in the ketone, it may present in the acid, it may present in the various acid derivatives like the esters, right? It may present in the your anhydrides, right? And your acid halides and your amides. So there are many questions based on this carbonyl groups actually, right? So here this is the frequency, stretching frequency in the IR spectrum, and this is the carbonyl frequency. Again, what we have to focus? We have to focus on this value 178, which is the functionality of the ester, and again 1717, which is the stretching frequency of carbonyl ester. So you have to look for the ester, guys. Okay, which one is ester and which one is not. So if you're looking for the ester, so this is you see here, this is double bond, this is oxygen, so this is the ester, this could be the answer. This is carbonyl, this is CH2 and this is CH2, this is not a ester. Since this is not a ester, you can immediately discard this option, this cannot be your answer. Now moving to the next one, this is oxygen and it is connected with the double carbonyl group, so this is the ester, this could be the answer. And see, this is another ester, this could also be the answer. But guys, you can see you can immediately discard this option D also. Why you can discard this option D also? Because in the option D you are having this CH, this is CH2, so I can write it as CH2 and this is CH. So you should in the IR spectrum you should have the stretching frequency of this carbon, right? Double bond carbon, and this carbon double bond carbon stretching frequency is not there in that case. So you can immediately discard this open chain ester also based on your knowledge. Okay, and furthermore you can see here this hydrogen is very close to the carbonyl group, so this will have the little different chemical shift, right? And this carbon will also have the different chemical shift. Why? This should be the downfield because it is connected with the ester, and this should be the upfield. That means two carbons must have the significant difference in the chemical shift. But if you check the data here, so you have been given see 178 is fine for the carbonyl, right? But this 28 and 22, it is quite close, and these two peaks actually indicating that the two carbons are of the same kind, and these two carbons are not of the same kind in these two in this particular structure, right? Because it should be downfield, it should be upfield, so you can immediately discard this one. Now you left with the option number A and option A and option C. So in the option A, again what you can see here, two hydrogens are here, this and this, okay, and of course this is your CH3 and one hydrogen is here. Okay, so in that case you see this carbon is connected with the, here you see this carbon is connected with the oxygen, so it should be highly downfield. It should resonate actually very high, it should resonate very high, and this should resonate again, it should be downfield, but there must be the significant difference in the chemical shift of these two carbons. But you see these two carbons are quite close here in that case. Okay, so again you can discard the option A, you can discard the possibility of the option A also, so you can immediately strike out this option. Now you left with the option C, right? This is CH2 and this is also the CH2, right? CH2 and CH2. So these two carbons are actually having the same kind, almost the same kind of the environment. You can argue that this is the carbonyl group and this is the oxygen group. You know the oxygen group is highly electronegative, so it will cause the same deshielding for this particular carbon as this carbonyl will do for this particular carbon. So these two have the almost same chemical shift. So you can mark that out of these two, this and this, right? These this and this, it should have say your 28 ppm and it should have 22 ppm, and since this carbon is close to the oxygen, it should have the 68 ppm and it should have your 178 ppm. So option C in that case is looking the correct option, and indeed it is the correct option. So option C is actually the correct answer in that case. But see, option A, you cannot mark option A in that case, because in the option A actually, if you check the chemical shift of this one, so this would be this carbon would be somewhere around, say, here 40 ppm, okay, and this particular carbon which is connected here, it is somewhere around 70 ppm. So you know this is the quite large difference, and this difference is not there in the structure. So option C is the correct one. But please remember, to solve the problems of spectroscopy, you should have you must have the better idea about all the spectroscopic techniques and some of the stretching frequencies in the IR spectroscopy, and exact knowledge of the proton NMR spectroscopy, because see, most of the time proton NMR spectrum is sufficient to give the idea whether it is to interpret the particular compound. So it is my advice also, whenever you see the new question on the your combined structural problem, first of all you have to look for the proton NMR spectrum. It will give you the most accurate idea about the compound. If you have confusion after this interpretation of proton NMR spectrum, then you have to look for the IR, okay, or other NMR techniques. Okay, now moving to the next problem, what it says that, so my next problem says that the ratio of the relative intensities of the carbon signals in the first order spectrum of 13C carbon and of CdCl3 is, okay, this question is quite actually easy. So how we can solve this particular question? So this is the solution. What the question says actually, question says the first order spectrum, right? And first order spectrums is the kind of the spectrum where you can apply the n+1 rule, okay. And what compound is given here, you see, compound is like that. This is carbon, and this carbon is connected with the 3 deuteriums. This is the heavy hydrogen here, and this is your Cl, and you have to look for the signal for this one. So this is deuterium is NMR active, and this deuterium is also NMR active, this deuterium is NMR active. So simply what you can see here, this carbon can be splitted by the deuterium and the deuterium. If you apply the normal n+1 rule for this particular carbon, then you can straightforward say 3 + 1 equals to 4. That means 4 lines will be observed, but it would be wrong. Please remember, it would be wrong. So how it would be wrong? See, whenever you have the deuterium which is having the different magnetic moment quantum number, okay, so your splitting will be different in that case. So number of lines, how you can determine the number of lines in that case? Number of lines in the carbon spectrum when you have the nuclei which is having the magnetic quantum number is something different. So you will use this formula 2Ni + 1, okay. So 2 is the constant, N is the number of surrounding nuclei. Number of surrounding nuclei. Number of surrounding nuclei. So how many nuclei have surrounded this carbon? 1, 2 and 3. Okay. So immediately from here, what you can write? 2 multiplied by 3, and the value of the I. For deuterium, the value of the I is 1. Okay, please remember, for deuterium the value of the I is 1. So multiplied by 1 plus 1. So 2, 3 just 6, 1 just 6, 1 7. So you will have total 7 lines. So when you have the 7 lines, so you can immediately discard your option A, because it is having 1, 2, 3, 4, 5 lines. And option B you can discard because it is having 1, 2, 3, 4 lines. Okay. So out of the option C and option D, 1 would be the correct option in that case. But please remember, to solve this question, you have to have an idea about the Pascal's triangle, right? You should have the idea about the Pascal's triangle, and in that case, the splitting actually in this case of the deuterium, splitting is non-Pascal splitting. Okay. So if you know the Pascal triangle only, then you will be able to solve this kind of the question, otherwise not. So see what I can do, see I can make some space here, say, because I need some space to draw the Pascal's triangle. Okay. So how I can draw the Pascal's triangle, guys, you can see here. say this is 1, this is 1 into 1, okay. Now 1 plus 2 and then 1, that is 1 to 1. Then you can write 1 here, then this 2, this plus 2 plus 1, 3, okay. So you can write 3 here, then again 2 plus 1, that is 3 again. So you can write 3 here and 1 out of 1. Again you can solve like that. You put 1 here and then 3 plus 1, 4. So you can write 4 here and then 3 plus 3, 6. So you can write 6 here. Then again 3 plus 1, 4. Here you see 3 plus 1, 4. So you can write 4 here, and after 4 you will write 1 here. So 1, 4, 6, 4, 1. If you follow this pattern, then you will find 1, 5, 10, 10, 5, 1. And if you go further, then you will find 1, 6, 15, 20, 15, 6 and 1. So this is the Pascal's triangle. Here if you have the singlet, that is for 1 line, and this is for 2 line, this one is for 3 lines, this one is for 4 lines, this one is for 5 lines, this one is for 6 lines, and this one is for 7 lines, right? But in that case, please remember, in that case the splitting would be non-Pascal, but I have drawn the Pascal's triangle. So 1, 6, 15, 20, where it is 1, 6, 15, 20, 15, 6, 1. This is according to the Pascal. And I told you the Pascal's triangle, Pascal's in the splitting will not be followed in that case. So you can discard this option 4 and your option option C. Then option D is the correct answer in that case. Okay. So this is how you can solve the problem. Now moving to the next problem, what it says that okay, now this question, what it says that this question is again from, you can see again, I have moved to the December 2014 examination. I have completed the June 2014 examinations. Okay, so last two problems basically are from the were from the December examinations. So the following reaction gives a product, of course a racemic product, which exhibits the following NMR data: proton NMR, that means 2 proton singlet, and 2 proton singlet. That means you are having all the time singlet in the NMR spectrum. Both should correspond to the 2 protons. And carbon NMR spectroscopy 170, 129, 105 and 25. But this problem is not basically that difficult if you have the little idea about the stereochemistry of the product. Please focus here what the question is saying. You will have the product as the racemic product. Racemic product, that means you are having the 2 different isomers, R and S. You are having the 2 different isomers, R and S. So if you check the see, you can immediately discard this option. This cannot be the correct answer. Why? Because it is the CH3. So in the proton NMR spectrum, you should have the 3 proton singlet. But in the proton NMR spectrum, you are having 2 proton singlets, not 3. So you can discard you can discard the option A. Now moving to the option B. Option B, of course, this is these 2 are the hydrogens. Okay, but you see this hydrogen and this hydrogen having the same environment of this and this, so this will give you the only one signal. Of course, the one hydrogens, other hydrogens are also there, but as you can see, the product is the racemic. But this cannot give you the racemic product, because both COH are up, right? And in the second structure, both would be down, and the configuration would be the same for this one. So this cannot give this cannot have the isomer which forms the racemic mixture. So you can immediately discard option B also, right? And then you can check for the option C, right? Option C, right? Say this is hydrogen, both are of the same kind. This hydrogen should be the up and this hydrogen should be below. So in that case, you see this COH group is up, this COH group is down, and if you form the isomer of this one, so this should be down, this should be up. In the next isomer, this should be up actually. So this is beta, this is alpha. Alpha means below the plane. this is beta, which is above the plane. So this could form actually the isomer, which would be the different, and the product would be the racemic in that case. So this could be the correct answer, option C, but we have to check the option 3 also. So here you can see this is the double bond, and this COH is on the same side, this CH on the same side, that means it is the cis. Okay, so this, and again you can see, you can discard this one also. Why? Because it is CH3 here, and you are not having the data which is corresponding to the 3 proton singlet, so you can immediately discard option 3 also. So what you left with the option C. So option C is the correct answer in that case. So this problem is not basically related to your spectroscopy, right? But it is actually due to this one. Okay, so this is how you can form. So I haven't write the question actually. So basically, see, since I have written the following reaction, so I have missed actually the reaction in that case. So reaction was like that: you are having this, okay, and this, and in that case you are having oxygen. So this was the ester, just like that, and here the substitution of the bromine, and here also you were having the substitution of the methyl, and here also you are having the substitution of the acid. Okay, I hope it was acid actually, right? Like that. Okay, and you have heated this compound NaOH. So this is producing these compounds actually. Okay, so you have to select the racemic one. So option C is the correct answer in that case. Now moving to the next problem, what it says that, okay, in fact this would be my last problem. What it says, the question says, an organic compound C10H12O2 exhibit the following spectral data: IR 3400 centimeter inverse, and again 1600 centimeter inverse. Okay, and proton NMR 3 proton doublet, 3 proton singlet, 1 proton singlet, deuterium D2O exchangeable, of course it would be OH actually, then 1 proton doublet, right, quartet of the doublet, complex splitting, and J equals to 18, right? This should be helpful to you guys. This should be helpful to you. So you should remember this value. This is important. This part is very, very important. This part is important. This will suggest you the correct answer. Rest we will check further. So first of all, you see what is the value of the coupling constant here, 18 Hertz. And coupling constant is the 18 Hertz. And I am telling you, and in my NMR spectroscopy lectures, I have already told you the value of the coupling constant. So when you have your cis alkene, then you have the coupling constant 10 to 12 Hertz. Please remember, when you have your trans alkene, for trans alkene you are having the coupling constant between 15 to 18 Hertz. So here you see the not 15 to 18, it may goes up to 20. As I already told you, nothing is absolute in the NMR. So above 15 you can write, right, and below 15 you can write. So whenever you have this chemical, coupling constant, that means it shows the trans alkene is there. Now check which alkenes are trans. So this alkene is the trans. How trans? You can put one hydrogen here, you can put another hydrogen here. This is trans. This is hydrogen here, this is hydrogen. So both hydrogens on the same side. So this is the cis, and this cannot be the answer. Immediately you can discard this. And for this one, you see one hydrogen is here, another hydrogen is here, so it is trans. This could be the correct answer. And this hydrogen is here, this hydrogen here, so this is also trans. This could be the answer. So you can discard only the option B actually, right? Now option B cannot be the answer. Now we have to look for another option, which one actually is correct and which one is not correct. So since option B is not in the answer, so I can remove this option B because I need some space here. Okay, now I am looking, right. See this 3400 broad actually, see generally this is due to the OH. So OH is here, and this OH is here also, this OH is here. In fact, in that case, if I have written correctly, 3 OHs are there, right? If I have written correctly this particular formula, or may see, fine, it is quite fine, guys. So this option you can also discard. This option you can also discard. Why? Because in the question itself, what is written here? O2. It is written O2 here. But in that case, one oxygen, second oxygen, and third oxygen. So this cannot be the correct answer. You can discard this one also. So I can immediately discard this also. I'll remove this. Now there is a close competition between the A and C. Which one would be the correct one? Okay. So this was your C. Now we have to select which is the correct option. Okay. So what I can do, I can put my hydrogen here, I can put one hydrogen here, and I can put one hydrogen here. Okay. And if you focus here, what the question says, you can see here, at 6.8, one hydrogen singlet, 6.8, one hydrogen singlet. This singlet is possible in any option. We can check here. If I put hydrogen here, if I put another hydrogen here, if I put another hydrogen here, see, this cannot be the singlet because it will couple with this one, it will give you a doublet. This cannot be a singlet because it will couple from this hydrogen as well as from this hydrogen. This cannot be the singlet. And this hydrogen can also couple with this one, so this cannot be the singlet. So option C is also not the correct answer. Okay. But if you focus on this particular hydrogen, it is alone here. In this carbon we are having nothing. We are having nothing. In that case, again you are having no hydrogens. In that case, so it will give you the singlet. It will give you the singlet, and that singlet definitely would be 6.8 1H singlet. That means singlet which is corresponding to the one hydrogen, and it is at 6.8, that means it is on the benzene. So I hope this A is the correct answer in that case. So this question actually was easy. See guys, this is very important. Whenever you are solving the such kind of the problems, don't go for the each and everything to interpret, because in the CSIR NET examination as well as in the GATE examination, you require a lot of time to solve the question. So you must actually save your time also. Okay. So if you want to save your time, so you have to apply lots of things. However, there are various ways to solve such kind of the question, but I have actually taken the most fundamental types of the things actually by which you can understand the problem more briskly, and you can solve the problem more briskly and more easily. So that's it for today. So before signing out, again my request is that please share my content to the others also, and if you are new here and watching video for the first time, kindly subscribe the tetrahedron chemistry classes. I will meet you again in the next class with the 2015 problem. So that's it for today. Thank you very much.